My name is Eelco Visser. I'm a professor at Delft University of Technology, and today I'm going to talk about scope graphs, a new approach to name binding. Good to have you here too, Robert. All right, so suppose you have designed a language. You have an idea for a language, and so you have scribbled on the whiteboard, and you have figured out the syntax and your semantics. So this is not a new language. This is Andrew Appel's Tiger language, but we're using it as an example. So you know what your language is going to look like. Now all you need is an implementation. All right, so what do you need to do? Well, you need a couple of things. You need to build a couple of things. You need a parser, a type checker, a compiler, or an interpreter. And so that's the job ahead of you. Okay, so you start with parsing, and well, that's good because parsing we know how to do well, right? So you use context-free grammars to describe the syntax of your language. That describes sort of the textual notation of your language, but it also gives you a way to get an abstract syntax for your language. And there are good tools for turning grammars into tooling. So if you use a language workbench like SpoofX, then you type your syntax rules, and out comes an editor that is syntax aware and gives you syntax highlighting and all these things. And it also gives you an automatic mapping from text to parse trees to abstract syntax trees. And there's more stuff that you can get from such a syntax definition. You could get syntactic completions where your new users can discover the language by control spacing and getting, well, proposals for possible ways to write a program. And of course you get syntax checking in your editor. And so this is all very well understood, right? So we have this notion of separation of concerns in syntax definition, where we have a notion of a representation. So we have parse trees or abstract syntax trees that represent the results of parsing programs. And that representation is language independent, right? So we can talk about abstract syntax independent of particular languages. And then we have we have a formal notation for achieving these things. So we write down context-free grammars and maybe disambiguation rules, and that gives us all we need to define the syntax of our language. Right? So these notions give us a language for talking about syntax. Right? So it's the concept that we can use to exchange information about the syntax of a programming language. And just by defining, well, just using context-free grammars, what we get for free is a whole bunch of language tooling. Right? So tooling that is that you don't have to write specifically for your language, but tools can provide it for you. So from a grammar you can generate a parser, you get a syntax-aware editor, you get syntactic completion, formatters, and etc. All right, that's nice. So we've written a grammar for our language and we're done. We have an editor. And if you want to know more about this, then I'll talk at more length about the declarative syntax definition in my summer school lecture on Thursday afternoon. All right, check. We have a parser for a language. Now we just need to do the other things. But all the other aspects of our language implementation require name binding. And well, that isn't quite so easy as the syntax part. And so that's what I'm going to talk about today. So what is name binding? Well, name binding is the fact that so our parser gives us tree structures for programs, but in fact our programs are graphs because we use symbolic names to refer from one place of a program to another place of a program. Right? And it's convenient in text, but in order to semantically operate with these programs, we need to resolve these graph links. Right? So this occurs as variables, local variables in functions, or function calls that refer to function definitions, and we have to take care of scopes. Right? So we may have deeply nested scopes, and we may have to figure out in which scope a variable is defined, taking into account shadowing. But name resolution we also have to do for types, for type names, right? We can make type abstractions and refer to those. For record fields, and we may want to have to do type-dependent name resolution, where we figure out what a name points to by first figuring out what a type is. For example, here in this expression, origin.x, we would like to know what x is this name referring to. But in order to figure that out, we first need to figure out what this expression refers to. And that has a name, which refers to some declaration, which has a type, which we need to figure out what it points to. And then via that path, we can figure out what the record field the x points to. All right, so that's the idea of name binding. And now the question is, how do we define the name binding rules of our language? Or put otherwise, what's the BNF of name binding? Right? It would be nice if we could write down declaratively what the name binding rules of a language are, and from that generate a whole bunch of tooling. And that's what this is about. So what we would like to achieve is for name binding similar as what we have for syntax, namely a standard representation where we can conduct and represent the results of name resolution, and declarative rules that allow us to write down what the name binding rules of our language are, and then from that derive all kinds of language independent tooling. So to start with name resolution, that says, well, from the use of a name, what is the definition of the name? And from that we get code completion and refactorings and all kinds of other tools. All right, and so this talk is about scope graphs. That is our proposal for a common representation, so the ASTs of name binding. So what are scope graphs? Well, the idea is simple. We take a program, or the AST of a program, and we map that to a scope graph. And what is a scope graph? Well, a scope graph consists of scopes, which are these circles, which can be connected by edges. Scopes can have declarations. So these are pointed to by from a scope. And we can have references. References are names that point into a scope in which they are references. And then given a scope graph, we want to do name resolution. And name resolution is a matter of finding a path from a reference to a declaration. So if you fall asleep now, this is what you need to take away from this talk. But we'll go look into this into a bit more detail. So we have developed a formal theory around this idea of scope graphs. So there's a calculus of name resolution which tells us how to resolve names in scope graph. And it consists basically of 4 reachability rules, and we'll look at visibility later. All right, so how does this work? Let's start with the basics. So we have a program, and in these examples I'll be using subscripts for names. That is not to make these names different, but all the x's here are the same x, but at different positions in the program. So that's to distinguish occurrences in a program. So what we want to do here is resolve a reference, the reference x2 to the declaration x1. So in this particular language there's no definition before use. And these definitions are enclosed in a single global scope. So we represent scopes by these circles, and we define references by boxes with names that are pointed to from the scope in which they are declared. And we define references by boxes that point to the scope in which they are a reference. And then resolution is a matter of finding a path from a reference to a declaration with the same name, following these basic steps. So we can go from a reference to its scope, and from a scope to a declaration. And well, so that's a simple name resolution. Now let's look at more interesting cases. For example, lexical scoping. So another example program, we have two declarations again, but now one of the declarations is a function, and so fun here is lambda. So the y1 is the argument of the function, is not the name of the function. And so what we see is we have a global scope, and we have a nested scope, which is the scope of the function. So let's make the scope graph again. So we have a global scope with two declarations x1 and z1 and a reference z2, and we have a nested scope s1 with references x2 and this is easier, right? With the references x2 and y2 and a declaration for the lambda variable y1. And now to express the fact that the scope S1 is nested in scope S0, we add an edge from the child to the parent scope. So now in order to resolve names, we can use the same rules we used before. So the local reference Y2, we can resolve with the rules we saw before. But in order to resolve X2, we need an extra step, namely we can follow a path to a parent scope, and from there to a declaration. All right. Questions typically arises at this point. Yes.
Well, that's the time for the question. Do this because we talked about the time to ask this question, but it's something that you talked before. You talked about, for instance, you gave examples, field names, but for field names you need the type.
I will get back to that. Yes. Okay. Yes, definitely. Yes. All right. There's another question, but we'll come back to that question that you haven't asked. All right. All right, so lexical scoping is a matter of building up chains of scope, and you can search from outer to inner scopes, but you cannot, so the declarations in inner scopes are not accessible from the outer scopes, right? They're encapsulated. And now let's look at another typical phenomenon in name binding, which is modules and imports. So here we have two modules, A and B, and here's the scope graph structure for those modules. Right, so the module names are declarations at the top level, and each of the scopes defines a scope for the declarations in the module. Right, so here we have a declaration x1, and in module A we have a declaration z1, and these declarations are not accessible from outside. Right, they're encapsulated in the module. There's no path from scope S0 to declaration X1, so they're encapsulated. But what we would like to do, so modules encapsulate declarations, but what we would like to do is to make them available to some other modules on request, and that's what imports are about. So this import construct is, well, itself mentions the name of a module, so it's a reference itself. But now in order to make the declarations of scope of module A available in module B, we need something extra, and that is the notion of imports. And to model imports, we have a notion of associated scope. So with a name, we can associate a scope. So we associate the scope of a module with its module name, and an import. And an import is an arrow from a scope to a reference, and it's saying, well, we're going to import. The intention is we're going to import the declarations in a scope associated with the thing. Let's look at the rule. Right, so what we would like to do is resolve Z2 to the declaration in module A, and well, we can go to the module it's defined in, but then we get stuck. But then using the rule for imports, we can resolve this. So what we first need to do is, so this rule says, if we have an import of R1 in scope S, and we can resolve R1 to a declaration R2, and that has an associated scope SR. Then there's a virtual edge between scopes S and SR. Right, so now if we resolve A2 over here to the module name A1, then we get a virtual edge from the scope of module B to the scope of module A, and that allows us to resolve the Z variable in the module it is defined in. All right. So the final pattern is qualified names. So with import we said, well, we import all the declarations from a scope into another scope. Sometimes we want to be more precise and say we want to have a particular name from a scope. And that is what what qualified names does, right? So here we're saying module N defines some name, and it can define lots of names. We want to use a particular name. So we have a static access to the declaration S1 in module M1. So how to model that? So rather than importing all of module N1 into module M1, what we do is make this S2 a reference in an anonymous scope that doesn't, well, really correspond to a block in the program. And in that scope, we import the module N, and that allows us to then, well, resolve the module N to its associated scope, and then via the import rule, import a particular name from that module. All right. So these are the basic ideas of the resolution calculus. It allows us to, so we build up graphs that represent the name binding facts of programs. And using these rules, what we get is reachability in that graph. Right? So we can go from references to declarations, and these patterns allow us to model a wide range of binding patterns. But how about ambiguity? So that's the question I was expecting. So what if there's two declarations that can be reached from a reference? And to deal with that, we extend this calculus with the notion of visibility, where we can disambiguate between multiple possible paths for a reference. And so it doesn't modify the reachability rules, but it gives you a predicate on deciding between paths. And we'll look at examples of that. So first off, here's a basic occurrence of a possible ambiguous scope graph. So we have a scope with two declarations for the name X at different occurrences. And that means the reference X3 now has two possible paths, right? We can resolve it to X1 or we can resolve it to X2. And so this resolution is ambiguous. And what can we do about this? Yes. We could use the last definition, indeed, but actually that's a different pattern, because in this scope graph we've defined that these are declarations in the same scope, so they're the same. We cannot really distinguish their order, but indeed the pattern is saying, well, if you want to have definition before use, you could have two different scopes, and we'll see an example of that later. Basically, the LED pattern is an example of that, where you say, well, now we can distinguish. We want to prefer the one that's closer. We'll see in one slide. But in this case, we could say, well, this is just wrong, right? I mean, this is a scope and it has two declarations of the same name, so that is wrong. Still, we want to be able to have scope graphs that represent that kind of erroneous information, because real programs do have these kinds of errors. So we do allow these things to occur, but then we can decide, well, but this is wrong. There's two references. There's two paths for this reference, and so this is an error that you can display in your IDE. But sometimes actually this may not be an error. So this is OCaml pattern matching, and there you can have multiple patterns that define the same variable, and so a reference in the body of such a case would refer to either one of those depending on the pattern match outcome. And here you actually have an ambiguous resolution in this kind of fashion. So sometimes this may actually make sense. All right, so let's look at more interesting cases. So shadowing, for example. Right, so here we have a similar example as we saw before. We have two declarations, and we have a lambda, but now we have a nested lambda, and let's see, what is the issue here? Right, so there's a reference of x in the body of the inner lambda. And there's a declaration of x as the argument of this function, but there's also a declaration of x at the top level. All right, and we see that in the graph here. So we have a reference at the bottom, and we have a declaration in scope S1, which corresponds to the lambda, and we have an x declaration at the top level in scope S0. All right. Well, so applying the rules we've seen before, there's a path from x2 to x3, and there's another path from x2 to x1. Right, so there's two reachability paths, and now we could try to modify our reachability calculus to try to exclude this case. But instead we say, well, we leave this reachability calculus alone, and what we instead do is distinguish between the paths. And so we can define all kinds of policies for defining shadowing-like situations. And so what we want to do here is define a specificity ordering that compares paths. And the specificity ordering here says that we want to prefer local declarations over declarations that we find via a parent edge. And then we transitively close that. And that means that the red path, in this case, is more specific than the blue path. It's not necessarily the case that the paths are shorter, as we'll see in a bit. So the red path is more specific, right? And that exactly corresponds to the notion we were expecting, namely that the inner lambda shadows the outer declaration. All right. Another kind of shadowing. So let's see what the situation is here. So here's the scope graph. It's a bit similar to the modules we saw before. But so we have a module A and a module B. Module A defines Z as we saw before, but now we also have a declaration of Z at the top level over here. And so we're interested in the resolution of Z2. Well, so this is an example. This is a question I asked at the exam. And so what does Z1, what does Z2 refer to? And of course, well, by name you say, well, there's two possibilities, right? It can be Z1 and Z3. So we can see, well, is there a path to both of these? And if so, which one would we prefer? Or which one would you prefer? That's true. Yeah. Okay. All right, so indeed, there's two paths. So one, as we saw before, via the module import of module A, and the other goes to the parent and reaches there right. So Z3 is in the lexical scope of the module, so that's where we could reach it, and the other is the import. So now you could say, well, you could argue about what is the right thing to do. And so we don't build in this choice in our calculus, but we allow the definition of a policy. And again, that's using specificity rules. And here we're saying, well, we prefer imports are preferred over parents. So if you import something, that is better than if you get it from your lexical context, because you're probably importing it specifically, so that's what you want to achieve. Probably you can also make the counter argument and say that you would prefer your lexical, the thing you find in the lexical context. But in this case, using this policy, what we get is we prefer the red path over the blue path. But we could also reverse the rule, and then we get parents shadow imports. Or we could leave out this rule, and then this situation would be ambiguous. And that would mean it's an error if something occurs both in the lexical context and in the imports. So you can play with these rules to tune the binding rules for your language. I completely forgot to turn this timer on, so if you can keep track. All right, so here's another variant. So we said imports shadow parents, but we can also say that we have, instead of imports, we have includes. Let me reconstruct. So what is this about? This is about the situation we want to resolve Z2, and we could either resolve it to something that's in our own scope, or it's in a module that we import. And so if we say that we prefer local declarations over imports, then we would prefer the resolution of Z2 to Z3. But if we would say, well, we have an include policy, that means we don't specify the specificity ordering, and that would mean we don't make a choice between these two situations, and that would give us an error in our IDE. All right, another interesting situation, and the example is a bit contrived. So this is a variant of the qualified name situation. So we have we're using this qualified name S2, and what we're saying is give me the S from module N, right? But it happens in this case that module N doesn't have an S, but there is an S in the lexical context of N. So there is a path that says, well, go from S via the import of N to its scope, and then take the parent edge to the enclosing context, and there find the definition of S. And so the example is a bit contrived because the scope that we're doing this in is the same scope as the lexical context of the module, but suppose you're importing some module from somewhere else, and it has a lexical context, and you're trying to get a member of that module, but it doesn't have one, and so that means you get one from the lexical context. Is that a good idea? Maybe not. And so we would like to be able to model that in our policy. But again, you may want to say, well, yes, that's an excellent idea. But let's suppose we want to forbid that kind of situation. What we can do is define a well-formless predicate on paths that defines that paths can have a certain form. And in this case, what we're saying is paths should have this shape. So you go from a reference via a chain of parent edges, and then possibly a chain of import edges to a module, and there you find a declaration. But what you cannot do is go to through an import, and then through a parent edge. So that forbids paths of this shape, and so it doesn't allow you to go to the lexical context of modules. 10 minutes? All right. And there's a couple of more of these patterns, and let me skip those. Well, there's only one. So the basic idea now is our calculus for name resolution. So we have reachability, which allows us to find paths in a scope graph from references to declarations. We have a well-formless predicate, which allows us to define a predicate on a regular expression on the labels of paths, and that allows us to forbid certain patterns or allow particular patterns. And we have this notion of a specificity ordering on paths that allows us to choose between paths, and that allows us to define shadowing policies. So that's the basic idea of the resolution calculus. And these were my requirements, right? So what I would like is a similar declarative situation as we had with syntax. So a representation that allows us to reason about name resolution. So that's what I've just shown. Scope graphs are this representation to represent the name binding facts of programs, independent of the particular language. And now we can define policies for visibility in such scope graphs. The next step is we would like a language for describing these things, similarly as we have context tree grammars for syntax. And for that we have designed a constraint generation language that maps abstract syntax trees to constraints. So what's the architecture? We take a program, we parse it, get an AST. From that AST we generate constraints, and these constraint generation rules are language specific. That's what the language designer expresses. And then given a set of constraints, we resolve these constraints, and that gives us a solution, and that operation is language independent. So we can reuse this architecture for a range of languages. So let me explain how this works. So basically the scope graph constraints correspond to the elements of scope graphs. So we can create new scopes. We can make edges between scopes that are labeled. We can declare a declaration, right? So here we're saying X is a declaration in scope S in the namespace N. So I haven't talked about namespaces, but you might want to distinguish functions from variables, and namespaces allow you to do that. The other way around is a reference. So here X is a reference in scope S in namespace N. And then we have a resolution constraint. So these constraints all are basically building up a scope graph, and the resolution constraint says, well, given this reference X, find me its declaration D by finding a path in a scope graph that is visible, etc. So these are the basic constraints, and then we have constraint generation rules that say, well, now give me the constraints for this expression given this scope. So let me illustrate you how that works. So here we have a program, we map it to its AST, and what we're going to do is build up, well, we have a scope from the context, and what we're going to do is build up the scope graph given constraint generation rules over here. Right, this constraint generation rule matches our let binding structure. Right, we have a let binding with a variable declaration and a body and some scope S. So what we're going to do is create a new scope as body. We make an edge to its outer scope. We declare X as a declaration in that body scope. And then we recursively generate constraints for the expression over there, so the initialization expression. And note here that we are using the scope S to generate those constraints, right? Because we then encounter the variable X over here, and for variables we have another constraint generation rule that matches on vars. And what it does is says, well, we generate a reference in scope S prime, so that's the scope S that we had there. And it requires us to resolve that reference. So in this case, we see, well, this x in this initialization expression, well, doesn't resolve to anything we know here because it's something, well, that it's free in this expression, right? Now, when we recursively apply that to the body of the LED, we may go down and generate some more scopes. We use the same variable rule, which now generates a reference for x in this scope, which we then resolve to the reference in the LED binding over here. All right, 5 minutes. All right, so how about types? Well, we can, our constraint language also gives us type constraints. So what we can do is say, well, the type of a declaration is some type expression. We have type equality, subtype, and well, there are possible extensions. And then we can define the typed constraints. So basically, it's the same constraints, but now we associate types with expressions and with declarations and references. And this allows us to resolve the types. This resolution here resolves the declaration of the variable x over here, and this constraint retrieves the type of that declaration, which is then the type that we infer for the variable. So in this way, we can define a constraint generator that gives us the constraints for a program that, when solved, do both name and type analysis for our program. So now I have a more interesting example, which is type-dependent name resolution, which is exactly sort of the interesting case, but I'm going to skip that in the interest of time. But if you're really interested, then crash my summer school lecture on Thursday, and I'll show that. All right, so what do we have? We have an approach for declaratively defining the name binding of programming languages. That consists both of a representation, scope graphs, and a declarative language in which we can define, by means of constraint generation rules, how we map ASTs to scope and type constraints. And this gives us a language for talking about name binding in programs. So given these definitions now, what we can do is generate all kinds of language-independent tooling that works with types. And so we have implemented this approach in the SpoofX language workbench. And so you write your constraint generation rules, and what you get is not only an editor that's syntax aware, but also an editor that is type and name aware. You can do navigation, it does name checking, etc. We're applying that to a bunch of languages, so we're slowly scaling up to more realistic things. It's still a work in progress. We also have an approach to connect this to semantics of programming languages, more in my summer school lecture. And so what's the status? So we have a theory that's this resolution calculus that gives us name binding and type constraints, and a name resolution algorithm that is sound with respect to the calculus. And we have this mapping to runtime memory layout. And we have a language for defining the name binding rules called enable2. And we have tooling to go with this. So we have a solver that's now getting acceptably fast. Well, acceptably slow, I guess you should say. And this is integrated in the SpoofX language workbench, where you can use it, and you get editors with name and type checking and navigation. And so this has, so what are the limitations? It's a domain-specific model. So what we can do, so the practice for name binding is Turing-complete algorithms and compilers. We cannot hope to cover all of those algorithms. So this really is kind of a normative model that says, well, this is what name binding is. Now the question is that adequate, right? And that requires experimentation. I think it does cover sort of sane name binding models. I think that's a good thing. Just like using context-free grammars for your syntax gives you a sane model for the syntax of your language. So there's still room for future work. So these scopes are really interesting, it seems, as a model for structural types, but that requires operations on comparing scopes. We are still struggling with generics, but there's an idea to use dependent object types. Inspired by dependent object types, there seems to be a solution there. We're working on type soundings of interpreters automatically, and that is progressing well. And there's a bunch of things to do in getting tooling more performant, doing incremental analysis, etc. So to conclude, I've presented scope graphs as a solution for name binding. What I hope that this will provide us a common cross-language understanding of name binding and a foundation for formalization and implementation of programming languages. And I would be very interested in your feedback offline or otherwise. And thank you. I guess we're out of time.
We can have one question. So let me ask by giving you one example of dirty hacks that may be done in some languages, asking whether this could be translated. Imagine that in a function, if it declares a return type, you want to resolve the identifier result to a synthetic variable of that type of the function. Is your approach able to do this?
Yes, that's fine. You can just make up names. They don't have to come from the program. Yes. That's it. All right. Thank you. Of particular languages. And then we have a set of we have a formal notation for achieving these things. So we write down context-free grammars and maybe disambiguation rules, and that gives us all we need to define the syntax of our language. Right? So these notions give us a language for talking about syntax. Right? So it's the concept that we can use to exchange information about the syntax of a programming language. And just by defining, well, just using context-free grammars, what we get for free is a whole bunch of language tooling. Right? So tooling that is that you don't have to write specifically for your language, but tools can provide that for you. So from a grammar, you can generate a parser, you get a syntax-aware editor, you get syntactic completion, formatters, and etc. All right, that's nice. So we've written a grammar for our language, and we're done. We have an editor. And if you want to know more about this, then I'll talk at more length about declarative syntax definition in my summer school lecture on Thursday afternoon. All right, check. We have a parser for. My name is Eelco Visser. I'm a professor at Delft University of Technology, and today I'm going to talk about scope graphs, a new approach to name binding. Good to have you here too, Robert. All right, so suppose you have a design to language. You have an idea for a language, and so you have scribbled on the whiteboard, and you have figured out the syntax and your semantics. So this is not a new language. This is Andrew Appel's Tiger language, but we're using it as an example. So you know what your language is going to look like. Now all you need is an implementation. All right, so what do you need to do? Well, you need a couple of things. You need to build a couple of things. You need a parser, a type checker, a compiler, or an interpreter. And so that's the job ahead of you. Okay, so you start with parsing. And well, that's good because parsing we know how to do well, right? So you use context-free grammars to describe the syntax of your language that describes sort of the language. Now we just need to do the other things. But all the other aspects of our language implementation require name binding. And well, that isn't quite so easy as the syntax part. And so that's what I'm going to talk about today. So what is name binding? Well, name binding is the fact that so our parser gives us tree structures for programs, but in fact our programs are graphs because we use symbolic names to refer from one place of a program to another place of a program. Right? And it's convenient in text, but in order to semantically operate with these programs, we need to resolve these graph links. Right? So this occurs as variables, local variables in functions, or function calls that refer to function definitions, and we have to take care of scopes. Right? So we may have deeply nested scopes, and we may have to figure out in which scope a variable is defined, taking into account shadowing. But name resolution we also have to do for types, for type names, right? We can make type abstractions and refer to those. For record fields, and we may have to do type-dependent name resolution, where we figure out what a name points to by first figuring out what a type is. For example, here in this expression, origin.x, we would like to know what x is this name referring to. But in order to figure that out, we first need to figure out what this expression refers to. And that has a name, which refers to some declaration, which has a type, which we need to figure out what it points to. And then via that path, we can figure out what the record field the x points to. All right, so that's the idea of name binding. And now the question is, how do we define the name binding rules of our language? Or put otherwise, what's the BNF of name binding? Right? It would be nice if we could write down declaratively what the name binding rules of a language are, and from that generate a whole bunch of tooling. And that's what this is about. So what we would like to achieve, the textual notation of your language, but it also it gives you a way to get an abstract syntax for your language. And there are good tools for turning grammars into tooling. So if you use a language workbench like spoofx, then you type your syntax rules, and out comes an editor that is syntax aware and gives you syntax highlighting and all these things. And it also gives you an automatic mapping from text to parse trees to abstract syntax trees. And there's more stuff that you can get from such a syntax definition. You could get syntactic completions where your new users can discover the language by control spacing and getting, well, proposals for possible ways to write a program. And of course you get syntax checking in your editor. And so this is all very well understood, right? So we have this notion of separation of concerns in syntax definition, where we have a notion of a representation. So we have parse trees or abstract syntax trees that represent the results of parsing programs. And that representation is language independent, right? So we can talk about abstract syntax independent